Okay, so we are on to box plots. So box plot is going to use that whole 5-number summary. So a box plot is a graph that represents the 5-number summary along with some additional information about the data set. So there are several different kinds of box plots. The one that we describe here is called a modified box plot. So what a modified box plot is going to do is it's going to make a box that represents your Q1, your Q2 or your median, and your Q3. So it's going to split it like this. Then you're going to make these whiskers, and these whiskers stop at what would be your lower, or what would be a value inside of, smallest value, smallest data value, greater than the lower outlier boundary. And this right here is a value that is less than the upper outlier boundary. So it is basically a data point that fits within those boundaries. It's the last one on both ends. Then if we have any outliers, we put little X's by them to represent them. So this represents those students in January who are missing several days. So when we were figuring out the lower outlier boundary, we had, what did we have? 45 plus 20 minus 21, and we had 26. And then the upper outlier boundary, I'm trying to remember off the top of my head what it was 80. So when you're trying to arrange this data, the smallest value we have in this boundary is actually your smallest data point. So that's why we stop here at 41. Then on the other end, 77 is my largest data point before I hit this boundary of 80. So I stop here at 77. And then the rest of this is just going to be your quartiles. So as you see over here, my Q1 is going to be at 45, which is where you see it at. This is my Q2 or my median, which was 51. And then this over here, my Q3 is going to be at 59. This 100 was an outlier, so we put an X right here to represent it. Okay. So sometimes we'll have this data that's going to have an outlier in it. Sometimes what it is we're just going to go out to our minimum and maximum values for our whiskers. But what we know is that each one of these areas is supposed to represent 25% of all my data. So what that's telling me is that here, my data is very, very clustered, and here it's very spread out. So if I was to draw a distribution for this, it's going to be skewed because we have this one long part right here. So we see my data humps up a lot here. Most of it's in this area, and then it sort of tapers off in this direction. So box plots are going to help us figure out how the data is going to be distributed. So if you could take a moment, make a box plot for this data. So just a reminder, I have it still here, and we don't really need them in this case, but if you're looking for that upper outlier boundary, that was 36.85. So that means this is the last data point before we hit that boundary. And at the other end, I'm trying to remember exactly what it was. That's completely wrong. Okay, we got a 1.45 at this end. So this is the last data point. So in this case, we're going to hit the minimum maximum of my value. But like I said, just take a moment because we did find the quartiles before, and just, like I said, split this data up and make a box plot for it. So you need to make sure when you make that box plot that it's going to be sitting on a number line, or make sure that number line is actually scaled correctly. Okay. So my smallest data point before I hit my lower outer outlier boundary is going to be 17.5. So I'm going to start this data 15, 16, 17. 17.5 should be here. So that's one end of my data. The other end is going to be at 36.1 because that is my largest value before I hit that upper outlier boundary of 36.85. And that's going to be 5, 6, just a little bit right here. Okay. So then my next part is that my we're going to do the Q1 to Q3 first. So Q1 is at 19.5, so about here. And then my Q2 is at 24.7, so about here. Then if we look for, oops, that's my Q7. And then if I do my Q2 to my, let me rescale that just one more time. My Q2, the box is not sitting right. There we go. My Q2 to my Q3, which is at about 31, almost 31. We're going to do that. And then what we need to do is just make a whisker that goes out to the ends of my data. And that's what's going to look like. So as far as that Carolina wolf spider data, it's almost symmetric. We see it kind of a little bit more bigger on this side maybe than the other side. But it's almost the same on both sides. You could also argue that's a little skewed because this one tail is way longer. So you can also do box plots. So if you go into plots, if you put your data in your L1 and you go mark where it says shows that little box plot, so it gives you two ones. You want to take that first one, it will do a box plot for you. Oops. So let's just show you. Make sure that's sharing correctly. There, my stuff keeps freezing on my end a little bit. So if you remember, I have that. I can move out just a little bit so I can show you this. So this is that data on number of classes that somebody was taking in a semester. So if I wanted to do a box plot for this data, I'd go second Y, takes me to stat plot. Then we'll pick that first plot. So you first want to make sure that your plot is on. Let's leave it out here because it won't let me get closer. Then you want to go through and you see this is a modified box plot and the one next to it is a different kind of box plot. So we want the modified. Hit enter again. So we'll put L1, frequency 1, and then you're going to go to zoom and you want to go to zoom stat. And that will make your box plot for you. And that data also did not have outliers, so it's not going to show those outliers on here. But as you see, we get those quartiles. So that data, it had a Q1 at 1.5, Q2 2.5, and then my Q3 was at 4. We had a minimum of 0 classes and a maximum of 6. Okay. Oops. Something came up on my screen that moved everything. So box plots can be used to determine skewedness in data like we were talking about before. So if the median is closer to the first quartile than the third quartile, or the upper whisker is longer than the lower whisker, the data is skewed to the right. So what it's telling me is, like I said, that I have a lot more data. There's 25% of my data is here and 25 is here. So if we have 25 in this bigger box, this box is twice the size of this other box, that tells me that data is more spread out. So if you go and you compare here, what we're saying is that in this range from between 2 and 3, there should be a lot more data in there. And that same amount of data should be represented here. So if you stack these, they're about the same. So like I said, if I took this on top of here, ideally they're about the same size. Like I said, because sometimes you're going to have something, you know, like those 4s are going to be partly here and here. It's going to kind of mess that data up a little bit. Well, like I'm saying, these ranges should be kind of like you're thinking those areas should be matching each other, the area here and the area here, because they both represent 25% of the data. Same thing for the whiskers. These 2 whiskers here both represent 25% of my data. So the area that they're taking up with these bars should be approximately equal. So because this line is not small, it means I have to have bigger bars. Then over here, I have to have smaller bars because that same area is spread out over a larger area, a larger range. So it's enough to kind of tell me that the shape of my data should look like that. So what we're seeing here is you have a long right tail. So this data is going to be skewed right. Apologize, I have dogs freaking out right now. So same thing here. If the median is closer to the 3rd quartile than the 1st quartile, so like we see here, it's a little closer. We'll make these boxes match up again. What that means is that the box and this area and this area are supposed to be approximately equal to each other. But this is spread out a little bit more, so that data is going to be like spread out a little bit more. So the boxes should be a little smaller than the bars should be a little bit smaller because that same amount of information or data points is spread out over a larger location. Also, if your lower whisker is longer than your upper whisker, the data is skewed to the left. It's the same thing. What's in this whisker and what's in this whisker, let me do that again. These 2 whiskers should have about the same area in them as far as those bars are concerned. It's just this has a smaller whisker, so I should have taller bars to make up that area, and I have smaller bars for this area. Of course, this one has the outliers too. That's also part of that lower bar. So what we're seeing here is that our data is going to be skewed like this. So we're seeing that we have a longer left tail. That means that we're going to be skewed to the left. Okay, so we have just a question here. In a bit, we're going to go through and identify this again, but symmetric data. So if your boxes are about the same size, so your median's halfway between your 1st and your 3rd quartile, and the 2 whiskers are approximately equal in the length, that means we're going to be symmetric. So this is symmetric, meaning this should be symmetric. So symmetric box plots give us symmetric distributions for the most part. Okay. So this is a silly graph, but it was a good one I found. I thought it was pretty decent. The length of metal tracks and wrap tracks are displayed in the 2 boxes below, and we're going to answer the following questions. So we want to determine if the length of metal tracks is skewed left, skewed right, or bell-shaped. So if you look at metal tracks, like I said, we have this longer whisker here, meaning we have data spread out like this. For here, we have this whisker is a little shorter. So that same area has to fit in here. So it has to make us bigger bars. Same thing here. This is lower. Or this is a longer area than this over here. So what we're seeing here is that, like I said, because these are smaller ranges, but the same amount of data is in there, we should get a more bigger hump in that region. So I would say that this data, because my tail is going to be to the left, let's highlight it instead. I'm going to say that metal tracks are skewed left. Now, if we look at wrap tracks, we have a distribution that it looks like these boxes are about the same length. These whiskers are about the same length. So the area in these two whiskers would be the same. So we'd have pretty much a distribution that looked the same there. And the same thing with the boxes. The boxes have about the same range. So the areas in these should be the same on both sides. So we're getting something that is symmetric and bell-shaped. Okay. The other part of this is just being able to read the data. So that should be saying C and D on it. So approximately, we want to know approximately what percent of wrap tracks and metal tracks have a length over 4.4 minutes. So we need to find 4.4 minutes, which is about here. And we want to know approximately how many have a length over that. So remember that these boxes represent 25% of the data. The whiskers represent 25% of the data. So when we look at the wrap soundtracks, we got about 25% of wrap tracks are going to be over 4.4 minutes long. However, if you look at metal tracks, we got 25, 50, 75, 75% of wrap tracks. Oh, sorry, metal tracks. 75% of metal tracks or over 4.4 minutes long. That actually reminds me, I was listening to an Iron Maiden song the other day, and like the track was 13 minutes long. So yeah, I can kind of see that the metal tracks do sometimes tend to be longer. Iron Maiden is like maybe it's like early metal, but it still kind of counts. So approximately 1% of length wrap track. Approximately what percent of length of wrap tracks are less than the median for the length of wrap tracks, or metal tracks. So we want the median of metal, which is here. So if we look at that, we can see that looks like pretty much all of wrap is going to have track lengths that are less than what the median is for metal. So 100% of wrap tracks have a length less than the median length of metal. Okay. So like I said, just a little bit of practice of what it's actually like. The purpose of these box plots is sometimes to actually to compare data to each other. So we can, like we're looking for those areas, like we were doing like 25% or 75% or 50% here. So we can actually use that to compare two data sets. So a lot of times they use box plots to compare two different data sets to kind of see how they compare to each other.